bienvenidas esta noche por la nueva lección. Okay, so let's. Oh, good to see you, everybody. I like to see you all energized. That's great. All right, so we have a very, very dense schedule today, but it's a fun case, I promise. This one is actually great and fun to work with, because in the past students liked it very much. So I know you're going to love it. I hope you're all doing great. I'm doing fine. Little bit unusual to be teaching at night. After the first class that we had teaching at this time, we didn't have a chance yet. I see that, Luis, you like linear models. Yes, linear models, they are simple, but very effective and insightful. All right, so we're going to talk about a real case about house prices, okay? And this is a problem that it's relevant because it's a decision that at some point, many of us have to make during our lifespan. And it is to look for a place where to live, perhaps to purchase it, although many of us like to rent. And it's never an easy choice because very rarely we can have the house of our dreams where everything is satisfies our desires, you know, unless we are very rich. And so we always have to make compromises. And what does really determine the price of a house? There are many variables to consider. And today we are going to learn how linear models can help us making this type of decision, while at the same time, we learn some extensions of the basic linear model. In particular, we learn about variable transformation and interaction effects. What is a linear model? Very simply, a linear model is a model that where a response variable that is quantitative is represented as a polynomial, as a linear polynomial of predictors or input variables. And the output of a linear model will be the estimates of the coefficients that are unknown. That is, which variable has an effect and what size is the effect to determine the output variable, the response variable. And we'll see that, you know, the linear model in its basic form has to satisfy certain requirements, certain hypotheses that they are not always satisfied in real life with real data. And today we are going to try to learn how to manipulate some of the variables that we have to go back and meet those assumptions. So there is still hope to run our models. So the main goals of this case will be how to select and use appropriate variable transformations to connect our data, to correct our data so that it becomes suitable for linear regression. And also we'll discuss on whether an additional variable to introduce in our model is always recommendable. And furthermore, how can we study and introduce interactions that can exist between independent variables, between the predictors of your model? An interaction, we'll see, is the variable where there is a synergic effect of two of the predictors, or three or more. There are higher orders. And in a way, it's a variable transformation, if you think about it, because you are to basically use the original variables. So to introduce today's case, we are going to start with a real life scenario. And the story is that you've been hired as a data scientist by a large real estate company in Seattle. Seattle is a city in the northwest of the United States. It's a place where a lot of people would like to go and live. So the house price is notoriously very, very difficult. And it's hard to find a house at affordable prices. And there are some neighborhoods in particular where houses are very, very expensive. So it's an interesting case study. And your job as a data analyst is to assist residents. So think that you are in this real estate company that not only helps sellers to buy their house, but also buyers to find their ideal home. And your job is to assist the Seattle residents that are selling their home to determine what is a good price based on the characteristics of their property, on the characteristics of their house. You do not want the price to be too high because nobody will buy the house. At the same time, you don't want the price to be too low because otherwise your client would be losing money by selling at a price that is less than the market. Juan, you are already very ahead of the game. You're starting already with the logarithm and box socks and so on. And we'll discuss which one is more appropriate. And it's not always just a matter of trial and error. Actually, the choice of the transformation can follow some type of rationale. And this is why today's case we'll discuss these topics. So, how can you do your job at best? Well, you were giving a data set that contained past sales prices for houses, and each property has a set of characteristics. So you can say, okay, well, given the price, can I find what are the good predictors? And then eventually, when I develop a model, then without knowing the price, I can use these predictors to estimate an appropriate price. So this data set actually is publicly available. The developer of this case found it on Kaggle and includes sales prices of houses in the state of Washington. And in particular, we are looking at the county that is called King County, where the downtown Seattle is is located. And is notice that there are many houses in a big city, and so there are a lot of sales. So the data set is concentrated on a small interval of time. It's just 1 year of data, but as you can see, it's a very rich data set. And so if the goal is to predict price, we know that the most basic tool is linear regression or multiple regression model. What is the difference, by the way, just as a refresher from previous cases that you might have already seen? A single regression model is when you have one predictor for one response. A multiple regression model is when you have multiple predictors for one response. In this case, the one response is price. The multiple predictors we will see are the house characteristics. Then you have multivariate model, which you haven't covered yet, and is when you have multiple responses. So when you're trying to predict a set of variables at once. So just be very careful with the use of this terminology because they mean different things. And in this case, we will start, as always, with a simple exploratory data analysis to make ourselves familiar with the data set. Keep in mind that in the applied part, you will be actually required to have a little bit of fantasy and to personalize the model according to your liking and to your sensitivity as a researcher, right? Remember that models, there is never just a correct one. All models, by definition, are wrong because they are not the real representation of reality. But models are useful simplification of what reality is telling us. So sometimes it's actually useful to look at more than one model because different models might be telling us a different story. So for instance, think when you're taking a picture of a person, if you take a picture from different points of view, you will see an image that is slightly different. It's not the same thing as having the person around you and you can have a three-dimensional image. Well, models are a little bit like that. You have the complexity of data that only the data themselves can provide. but then the model can look at different characteristics of your data and it's telling you something useful, potentially useful. Then, of course, there are models that are bad and they are telling you nothing. And then, of course, those we don't want them, okay? So after an exploratory data analysis, we learn about variable transformations. So we'll discuss on why we cannot go ahead right away and use a linear model. And then we learn how to incorporate interaction effects, which is a type of, of variable transformation. All right, so let's start reviewing the columns of the data set and what they mean. The first column, as many times happens, is the ID. So it's the identification of the sale for that specific house. Notice that technically it's possible that the same house got sold twice within a year, however, it's fairly rare. So for all practical purposes, we can say that the ID is the ID of a particular sale or a particular house. Then we have the date, which is the date the house was sold. And notice that it's in a funny format that perhaps we might want to address. Then we have the price. So for instance, the very first house was sold for $221,900, okay? And it was a house with 3 bedrooms. That's the next column. And then you have bathrooms. How many bathrooms that house had. Now you will see that bathrooms is actually contains decimals, and it's because I don't know how it is in Colombia, but sometimes when the bathroom is a half bathroom, is indicated either as a 0.25 or a 0.5 bathroom. Typically, a half bathroom is a bathroom that only has the water closet and the sink, but does not have a shower, let's say. So it's bathroom for guests that are coming for dinner. They don't need to take a shower, okay? Then we have the square feet of living space. And I was raised in Italy where we use square meters, right? So if you want to have an idea, a quick conversion between square feet and square meters, just divide by 10, and it should give you like a reasonable approximation. So for instance, the first house is 1,180 square feet, should be about 100 square meters of space. And then you have a number that is square feet of the lot. That includes not just the living space, but also the garden or the yard, etc. Alejandro, a toilet is a bathroom, a half bathroom. Well, it really depends. It really depends on that. Typically, you indicate the word toilet to indicate a public restroom. So yeah, there are different ways that Americans like to call their services, service rooms. Then you have floors, the number of levels where the house is built. Then you have waterfront. Waterfront is a binary variable that is telling you whether or not the house faces the water, which can be, a lake, or it can be the ocean or a sea, etc. Then you have view. So view is an ordinal variable that goes from 0 to 4 and tells you how good the view is. I don't know who established this. Perhaps is something that the the real estate company themselves did. And then you have condition. Condition is another categorical variable that goes from 0 to 3, and this is based on the King County grading system. So a value of I think it goes up to 5. I'm not sure, but value of 5, I think it means very good condition. Level of 3, not so good, or average, and 1, not that good at all. Then we have grade. So this is an overall grade given to the housing unit based on the King County grading system. Then you have square feet above. Now, houses sometimes are built with a lower level, the basement, that's below the street level. And so here it's telling you how many what portion of the house is actually above the ground level. That means what portion of the house has actually windows, okay, or full-size windows. And then we have the square feet of basement. So that's how much space there is in the basement. Now, there are other variables, there, including the year that the house was built. Notice that here we have houses that were built, this very old, 1933. This one is newer, 1987. And then there is another column that is called year renovated. And probably here is talking about major renovation that house had to go through. Then you have the zip code, which is a postal area. Then latitude and longitude. These are geographic coordinates that pinpoint the location of the house. So the latitude would be the northing and the longitude would be easting. And then you have square feet 15 and square feet of living 15 and square feet lot 15. I suspect that I can't remember this variable. It's actually not even in the, we will have to click here for the full. There is a file, an entire file that tells you, like, you know, all the variables, but we are not going to use them anyway. This one's then end up with 15. It's probably some kind of transformation or normalization for the square feet of living space. Then you have log price, and we'll see why this is there, and the logarithm of the square foot of living space, and then whether or not the house was renovated and whether or not that house has basement. Okay. All right. Yeah, you can see that some of you already pulled up the file, but yeah, see there it doesn't say what square feet lot 15 is. Oh, is the square footage of the land lots of the nearest 15 neighbors. So that's actually very interesting because it's telling us whether or not the house is larger or smaller compared to the average size of the neighborhoods, of the neighbors. Yeah, the square feet living is the area that is habitable in the house. So it does not include the garage, for instance. It only includes the bedrooms, living room, etc. All right, so let's start with an exploratory data analysis. And let's start with price. So how many observations we have? So we have to take this number and move the comma 4 times. So we have 21,000 plus observations, 21,000 plus sales. And the mean is $540,000 approximately, with a standard deviation of, it's actually a very large standard deviation. It's $367,000. So that's very large because we'll see that there are houses that cost several $1 million. Okay, so the minimum is 75,000. The maximum is 7.7 million. So we have a lot of we have some expensive homes. And then we see also that the median is 450,000, which we can see is a little bit lower than the mean. So we already can spot the distribution of the price must be skewed. So let's take a look at the histogram of the price. Oh, showing too much. So when you look at this distribution, you see an histogram, and then you see a smoothed version of a histogram, which is called kernel density estimator. What can you say? Does this distribution look normal to you? And why not? Or why and why not? So tell me a little bit. What do you think about this distribution for price? That's right? Skewed, yeah, I agree. Positively skewed, indeed. Long tail. Carlos says looks like a log normal. Very good. So yeah, it's similar also to an F distribution. It's very similar to all the distributions that have long tails and that are skewed, like the gamma distribution or the log normal. And yeah, Javier, I agree. It kind of looks a little bit like an income distribution. That, of course, yeah, you have a lot of poor people, and then you have very few incredibly rich people. So we do have outliers. Notice that here we can see David is pointing out there are outliers, and it has a leptokurtic form. Yes, the kurtosis is also, yes, is not what we expect from a normal. And plus, it's a distribution that obviously is censored, right? Now, this is an important point. Probably more important than the skewness is the fact that this distribution of values is always positive. And that means that when you have a variable that is always positive, the normal has to be used with caution. And the reason is that, as you know, the normal distribution is defined between negative infinity and positive infinity. That means that we would be using, if we use the normal to the price, we would be using a distribution that contains negative values. This is problematic when you are building intervals, let's say for smaller prices, because you might end up with an interval that contains a negative number. That means that you would get paid to buy a house, which is very unrealistic. I never had anybody that would give me money and take their house. All right, so we can also see that the 25th percentile, so if we look at the interquartile range, we can also see that, you know, this, notice that the median and the 25th percentile are actually much closer than the median and the 75th percentile. So we can tell that there is a tail. Haunted house. Another way that we can assess this, there are many different ways to tell whether or not a distribution is close enough to a normal. One of them is to do the QQ plot, also called quantile-quantile plot. And it's a plot where you have the quantiles of the data, so they are called empirical quantiles, against the quantiles of the target distribution. In this case, the target distribution would be the normal, the distribution that you are comparing it against. If the distribution is sufficiently similar to a normal, these quantiles will lie on a straight line, on the 45-degree line, in fact. And before we try to interpret the QQ plot, consider a normal distribution and its percentiles. So this would be the first percentile, the second, etc. And here we have a sample of the first 100 observations. And therefore, each observation counts as a percentile. And as you can see, when you compare it to a normal distribution, it's, you know, reasonably close, because you can see that most of them are within the mass and so on. They were actually generated from the normal. And this is what it looks like when the data is well behaved. Okay. So if we plot the percentiles of the normal distribution against the percentile of the sample that we have obtained, we get points that are more or less on a straight line. When do they start deviating? Well, they start deviating a little bit in the tails, and that's just because those observations are very rare. And so you don't observe many of them, and sometimes when you observe them, they might be a little bit larger or smaller than expected. And you can see it here. Can you see this point here? This one was much larger than expected. It's almost in the tail, and it's this value right here. Okay, so this is when things look good. Now, in this case, we used data that we're generating from the normal that have the same mean and the same standard deviation. So we have a scatter plot that actually follows the y equal to x line. What happens if you generate data from a normal distribution that has different mean and different variance, but still normal? Well, all you can see, you can still see a straight line, right? But if you look at the scale of the x-axis and the y-axis, they are different. So it will not be anymore y equal to x, but it will be y equal to x times 10, I would say here, because here you can see that the scale is between 100 and 200, and for the y-axis is between roughly 1,000 and 2,000. Okay, so your equation in this case would be y equal to 10 times x. Still a straight line. So we don't need to care about whether or not the variables have the same mean or the same standard deviation, as long as they fall in the same line. Maria Paula, how do we analyze price? Because those are always positive. Yes, and this is what the goal of today's class is. What do we do with the prices? They don't look anything like this. By the way, here you will have some additional references for QQ plots. There is a video that was provided to you. Let's make sure that it's still there. Well, there is some advertisement here. I will let you explore it by yourself. And then there is a more technical presentation of QQ plots, where you actually have some formulas on how to calculate it, how to how to interpret it, and so on. So those are for those of you that are more curious and they want to learn more at QQ plots. So now we've seen in the ideal case, we put the theoretical quantiles of the original distribution, and then the empirical quantiles that were obtained from that distribution. So some empirical values. So let's go and check the prices. Are we close to this situation where the points are almost on a straight line? Well, let's see. This is what we have. These are the quantiles of a normal. So if you take a standard normal, you will see that the distribution has a lot of mass around 0, and then it tends to decrease, right? And you see that when it reaches -3 or +3, the density is almost 0. And let's look at the quantiles of the prices. Does it follow the red line? No, right? So what are we seeing here? What are we seeing is that there are no negative values. Notice that the points are pretty much here. They're very close to 0. So they don't go below 0, while the normal distribution does. Plus, there are way more prices that are larger than expected compared to a normal. So we do have a problem of a long, heavy tail on the positive part of the distribution. And we don't have a tail on the left hand because the 0 is the sensor value. You cannot have a price that is negative. Luis, what does negative theoretical quantiles mean? So let's look at the normal distribution. In this case, we have a distribution that is normal, but has a mean around 150 and so on. So this is centered around 150, but the standard normal, if you think about the standard normal, is defined, is centered at 0. So you have values that are on the left so they are negative, and values that are on the right, so they are positive. So actually, let me show you something from a normal distribution. Show you some. So Wikipedia is a good start. All right, in blue, actually in red, you have the standard normal. The standard normal is the normal distribution with mean 0 and standard deviation or variance equal to 1. The quantiles are the values on the x-axis, right? If I ask you what is the 50th percentile or the 0.5 quantile, it would be 0, right? Because the percentile, remember, is the observation that leaves to the left that x%. So -1, for instance, I think it's around the 25th percentile, right? So you will have, I know it's a little no, it's a little less. You will see that percent of the distribution will be left to the left. So if it's the 25th percent, it will be greater than 25% of the observation and smaller than 75% of the observations. So putting the quantiles would be the values that are observed on the x-axis. So of course, they can be positive or negative when you're dealing with a normal. When you're dealing with a price, though, no. When you're dealing with the price, you have a distribution of this type where all the quantiles are positive. They go from 0, well, actually, they go from 75,000 up to almost 8 million, okay? For the particular distribution of these prices. So here we can conclude, what is the conclusion of this? That the normal distribution is not a good distribution for this data set for the prices, okay? Now, exercise 2. Remember, when we talked about linear regression, we said that if you have just one variable to predict a response, the relationship between the predictor and the response should be linear. So in the plot below, we can see the relationship between house prices on the y-axis and the square foot of living space. What can you conclude? So, is this a linear relationship, in your opinion? I would like to hear your comments about this, because this is an interesting plot. So if we were trying to predict the price just based on the square feet of living space, we would do a good job. Sandra, more square feet, living space, more variability. Absolutely. But didn't we say that the normal distribution, the linear model should have constant variance? Yes, Victor, you said heteroskedasticity. That's one of the favorite words and strangest words in statistics. That's correct, is when the variance is not constant. Yes, Gabriel, there are some outliers. And then there is an outlier 14,000 square feet. Oh yeah, you're talking about this one. Well, this could be a very, you know, a building in ruin. I don't know. So the assumption of normality is not accomplished, but also the linear assumption here is in question. Look here how, especially for these prices here, the linear model is not a good predictor. It's really underestimating. Why is that? Well, the plot could be a little bit misleading because the size of the dots is fairly large, So what it's telling us is that there are lots of prices that are lower here, okay? So there are a lot of points that are not well captured. So in this sense, the relationship cannot be linear. So it's probably something that goes more in a curvilinear way. So, but it's not obvious. It's not obvious just because there are so many points. And what we can see that increases linearly is actually the variance. Nicholas, I really like that comment. The higher the price, the more variables affect the price in addition to area, indeed, because after a certain level, when you have a large house, then there are other things that determine the price. I agree. Perhaps when you're dealing with very small houses, unless you live in a very expensive area, if you have a small house, it's not going to cost too much anyway. But you know, there are exceptions. There are exceptions. For instance, if you go to New York, the location is probably the most important part in determining the price of a house. And you might find houses that are, or apartments that are very small and they are extremely expensive. Let's say if you are near one of the zones of the city that are more sought after. All right, so Edison, maybe if we apply a square root transformation, maybe, after all, we are going to talk about transformations. All right, we have seen, number one, the distribution of prices is not normal. And that can be contributing to that effect that the scatter plot looks like it's fanning out. Yeah, Herman, that seems pretty correct that those are the celebrity houses. And there are actually several that like to live in the Seattle area. You know, Seattle is still a center for music production. I mean, not as big as Los Angeles, but it's still very popular. Artists, many celebrity artists live in Seattle, and then of course is the headquarters of some of the biggest companies in the U.S., including Boeing and Amazon, if I'm not mistaken, started in Seattle, and Starbucks probably. I can't remember. Oh, there you go, Hector. You beat me. Amazon, Microsoft, and Starbucks. Yeah, of course, Microsoft as well. And in exercise 2, we saw these characteristics that make you question the idea of linearity and the idea of homoscedasticity. Homoscedasticity means that the variance is constant. Clearly here, it's not constant. What can we do in this case? Well, that's why we need variable transformation. What is a variable transformation? A variable transformation is the application of a mathematical function that transforms the original values in such a way that the assumptions are then more closely met. And typically you would like a transformation that does not alter the order of the variable, typically, but we'll see that there might be some exceptions. So for instance, the logarithm is a classic because it preserves the order. It's an increasing function. And what the logarithm does is it makes the smaller values proportionally larger and the large values smaller. So it has kind of a compression type of effect, okay? So what you would see if you take a linear, we're going to see what happens when you take a logarithm, but you will see that those extreme values will be less extreme, much less extreme. Other choices, though, the logarithm is not the only one. There is a quadratic. So if you take the square of a certain variable, a cubic, or the square root, or the sine and cosine, depending on if you have certain types of variables that are cyclical. There are many different transformations that you'll be dealing with. And those are the so-called trigonometric functions. So let's start with the simplest. And this is one that is used, I would say 90% of the time, to transform the response variable, and it's the logarithm. Now, we took the log of the house prices And we created the plot below and the table. So what do you think? Did we improve on our previous situation? This is the distribution of the prices now. Andres, we are going to discuss about how to interpret the results on the linear regression, so no worries about that. And when it's not a good idea to use log to normalize the data, well, not all data that is non-normal looks like a log. So in that case, it's not appropriate. But we'll see that we have some tools to decide which transformation to use. Serio is way too much close to the linear. No, it's a good thing, right? So you have actually something that looks quite normal. So let's check now some descriptive statistics of the data. And here you can really see how the compression effect that I was telling you about. Notice that the mean is 13.04 and the median is 13.01. So now we have a distribution that is much more symmetric, right? The mean and the median are much closer. But then we go and check the minimum. It's not that far away. It's about 11. And the maximum is almost 16. You can clearly see that there is still a tail effect. So that's still there, but it has very, very small probability. And there you go. So this is what the transformation of a variable to a logarithm. Now, for those of you that said that the distribution of prices looked log normal, that's exactly what it means. It means that if you take the log of the prices, you get a normal. So that's what a log normal distribution is, okay? All right, so let's talk now about what are the implications in terms of our linear model. Of course, we can. One question that can always start at this point is like, okay, well, do we only transform the response, or can we also transform the predictors, the explanatory variables? Well, the answer is yes, you can transform the explanatory variables. However, the reasons would be different to do that. Typically, we want to do that if we want to favor a particular type of interpretation that we are going to discuss. Another reason could be when you have data that are on very, very different scales. Then in that case, you might want to transform the X variables sometimes for stability in computation. There are many different reasons. But let's, without giving further details at this point, let's transform both the price and the explanatory variable, the square feet of living space. So a simple linear regression will look like the following. Your response, your Y variable, log price, beta 0, the so-called intercept, beta 1 is the slope, the log of the square feet of living is the predictor, plus epsilon. Epsilon is, of course, the random error. Applying this log, do we lose information? No, you do not lose information because the log is a fairly harmless type of transformation. You're not sacrificing anything. It's just your interpretation that will change, as we will see. So no worries, okay? There are sometimes, okay, one thing that I need to disclose is the following. To take the log of a variable, that variable has to be positive, cannot be equal to 0. Because we know that the logarithm of 0 is negative infinity, right? In the case of the prices, we do not have any price that is equal to 0. So when you have zeros in your data set, you cannot directly apply the log. You might want to alter the zeros in one way or the other, or use a different type of transformation or a different type of distribution, okay? Maria Camila, is necessary apply in the y variable? Well, in this case, is strongly recommended in order to get to a situation where things are more similar, more close. They are closer to the assumptions of the linear model. So let's take a look at the previous model, right? At the previous relationship. Now we have the square feet of living space on the x-axis after being transformed, log transformed, and the log price on the y-axis. Remember, this was the plot where the untransformed variables, they were fanning out. So we had a problem of increasing variance. Do you think that we addressed some of it? Yes. Yeah, Sharon, we'll discuss about how we decide on the transformation. So far, we are starting with an example first. Now the variance is fairly constant. What about the functional relationship? What do you observe that is a little bit strange between the red line and the cloud of points? Matteo, yes, we can add regularization, but I mean, first we need, before we start running, we need to first learn how to tie our shoes. That's what my professor used to say. Yeah, the slope is interesting here, right? We can see that the way that the points are centered around this line doesn't seem to be exactly symmetric, right? At least in terms of range. We know that probably here there are many more points, okay? And that's what's keeping, like, the line a little bit lower. So we might have to think about this a little bit, right? Otherwise, we would have expected a line that perhaps would go a little bit in this direction. Anyway, let's take a look at the output of the least square regression. So we have an intercept that is estimated as 6.7, and the slope is 0.8. If you have already discussed what R square is, we can see there is 0.45. So we are saying that the logarithm of square feet of living space explains about 45% of the total variability of the log price. Now, in the original scale, how do we interpret the slope? The slope would be the change in price if we increase the predictor, that is the price, sorry, that is the square feet of living space, by 1. However, here we don't have, here we have transformed variables. So in this case, we have a so-called log-log regression, and we have to change the interpretation of the slope beta 1. When you log transform, the coefficient beta 1 should be interpreted as a percentage change in the dependent variable that is associated with 1% change in the independent variable. So that is, here we are saying, if the log of, if the dependent variable, so the square feet of living space, increases by 1%, we will see a price increase of about 0.8%. So that gives us the rate, and it's called elasticity. Those of you that have studied economics, they will know that elasticity is basically, what we talk when we talk about prices and how the prices react for changes in demand and so on. All right. We have an appendix at the end where we can go and discuss mathematically why the log transformation leads to a percentage type of interpretation. Yes, Viviana, the elasticity is the percentage change divided by the percentage change. So it's the percentage change of the y divided by the percentage change of the x. Question, the x-axis is price per square foot of living space. No, yeah, the x-axis is the square, is the log of the square feet of living space. So this is the area, is the log of the area of the house, okay? And on the y-axis, you have the price of the house. What happens if we only transform the response? If we leave square feet of living space in levels, in its original scale? Actually, not much. Now the plot, notice that it's a little different. I actually personally like it a little bit more because it looks more symmetric around the line, around the regression line. However, here there are some distortive effects. And there is a change, of course, in interpretation, and we are going to discuss this case. This case is called semi-elasticity. So what we have here is a coefficient for the slope that is 0.0004. The reason why is that now, with the variable in levels, notice that the values are much larger. So we have houses that go from 0 to 12,000 square feet. Okay? And so this is called log level regression. So the dependent variable has been transformed, but the independent variable has not been transformed. So the coefficient beta 1 is called semi-elasticity. That means that a change in square feet of living space, a change equal to 1, notice that this will not be a change that is percentage. It will be a change equal to 1 in square feet of living space, leads to a percentage increase in price that is equal to this value right here. Specifically, we can say that an increase in living space by 1 square foot leads to a 0.04% increase in price. So if a house is 100 square feet, okay, and it costs $100,000, okay, if a comparable house that is 101 square feet, how much we would expect to pay for it? It would be 0.04% of 100,000, right? Which would be about $400 more, right? If I did my calculations correct. Natalie, how a house with 0 square feet can have a price? Not really. Okay, this is a very important question. Now, thank you so much for asking this question because it's a very good question. Now, let's go back to the price range. What is the minimum? Is 75,000. Do we have any information about houses that are cheaper than that, or that we should actually plot like the square feet of living space, but how can we, why do we get still a price that is positive, right? So, why is that? Well, the problem is that the regression model is not an extrapolation tool. That is, you cannot predict values that are outside of the observed range. And this is why we cannot really trust the linear regression for values that are smaller than the observed range and so on, because in that case, obviously, it would not be a good model. First of all, here you would need a model that actually starts at 0, right? You would need a model that starts at 0, but cannot be linear because then it would not interpolate the data well at all. So perhaps something that is curvilinear would be more realistic, but it's very rare that you find houses that are so tiny or houses that are so cheap that cost nothing, right? So this is why you have to all right, so yeah, so the 0.4%, yeah, I think you're right. It's $40, it's not $400. Matteo, sometimes I hear the linear regression can be used to predict. Yes, but typically you are predicting within the range. So even in this case, we are predicting, but we will be predicting houses for which we have observed some comparable range in terms of square feet of living space. So you are predicting, but you are not predicting outside of the feasible range. Yes, Nicholas, this model can only be trusted if houses have a price that is higher than $70,000, $75,000. Absolutely. Just we don't have information before what happens outside of that. But as you can see, the vast majority, they are. So, you know. Yes, Marcel, this is just 1 year of data. So yes, this is for the full data set. Yes, linear regression, just because, okay, think about the behavior of a linear line. What is the extreme of a linear line? A linear line shoots down to plus infinity, right? So how many data do you know that have that scale? So typically polynomials, they do not have, you know, a good representation of extreme data because they do not taper to an asymptote. They actually grow indefinitely, and they on both sides, really. So, you know, this is why the linear approximation typically is only valid for values that are within the observed range. There are some examples, for instance, in time series analysis, where you can actually predict outside of the range, but typically only short term. For instance, when you are looking at increase in number of passengers on airplanes, you can actually see the series that after you log transform it, that increases almost linearly. But of course, at some point, it will have to stop just because the world population cannot be larger than a certain amount. So there are some cases where you can extrapolate, but not on the very long range, okay? Jaime, if there is a little departure for normality, is not a problem. If there is a huge departure, yeah, of course. Keep in mind that we are dealing with real data. We are not dealing with data that are automatic, they are simulated from a true distribution. So we have to try to find what distribution matches our data in the best way. So comparing the plots of the log-log and the log-level model, which one is more linear? We can see that the log-log model seems to cluster more uniformly around the line of best fit, suggesting that the log-log model is more linear, and the problem is this part right here. However, for certain parts of the data, they seem to be clustering more correctly. So we might want to keep the log-log. So we said that how do we choose a transformation? We said that another possible candidate could have been the square or the square root or the cube or the cubic root, etc. In this case, it was relatively straightforward. When you have positive values and you have that type of distribution that looks like a log normal, well, when it looks like a log normal and sounds like a log normal, probably is a log normal. But it's not always the case. And when it's harder and you need a little guidance and say, well, okay, both these transformations, they improve marginally, but they are not satisfactory. That's where you use the so-called Box-Cox criterion. This is a mathematical function that gives you a number when you apply it to a variable. And this number is represented by the letter lambda, and basically tells you the type of transformation that you should use. So the box-Cox transformation has the following formula. Let's see if we can find it here. Well, here is just giving you the transformation, but I'm looking for the actual formula. Anyway, yeah, here there is a video, but I want to just show you the formula. We also have something at the end of the case. Okay, box-Cox. No. Here it is. The box-Cox transformation is the following. So if lambda is different than 0, this is the formula. You take y to the power of lambda -1 divided by lambda. And how is this lambda found? Well, the lambda is found by an optimization process. So is the variable that ends up looking the most similar to the normal distribution. So for instance, if you get a lambda equal to 3, it means that you should take the cube of your response. If you have 2, is the square. If you have 1, leave it like it is. It's good. If you have 0.5, it will be the square root. If you have 0, that's the log. If you have -0.5, it becomes the reciprocal of the different transformations that we have seen, so the inverse. In this case, for our prices, we found a box-Cox lambda equal to -0.23. Could we take 1 divided by y to the power of 25? Yes. What would be the problem with that? Well, the problem with that would be that it would be extremely hard to interpret in terms of scale. However, with the log, this is a value that is reasonably close to the log, to 0, that gives you the log. And we can interpret it in a nice way using percentages, rather than using a transformation that might be a little bit closer, but is uninterpretable. And a lot of these are very difficult to interpret. Like, for instance, for -0.5, interpreting 1 over the square root of y, it's a challenge in terms of units of measure and so on. So, Victor, how do you get the lambda value? Well, there is an optimization process that goes behind it and finds the value that is optimal for that particular vector of values that you are providing. So in this case, we are reassured by the box and Cox transformation that the log is a good choice, just because the lambda value is very close to 0. All right. So now that we have learned one thing or two about variable transformation, let's dig deeper in terms of creating a realistic model, right? Because we said that size is not everything when you're buying a house. You're looking at many other things. So what are variables that you would like to consider among the ones that we have seen? Francis, sometimes imagine that our box-Cox transformation would have been given us a lambda of 2.9. Well, in that case, you have to use the cube, and then you will have to just make sure that you are interpreting the results correctly in the scale of the transformed variables. Definitely number of bedrooms, number of bathrooms, location. How do we use location in this case? Perhaps the zip code, right? Waterfront, yes. In the morning when you wake up, you want to see a beautiful sunrise. on the ocean, you gotta pay for that. I mean, there are more variables that play a role that are not captured in this data set. For instance, proximity to schools, to hospitals, to grocery stores, to entertainment places, or to restaurants, to bars, clubs, gyms. So, William, no, the variable view is related. It's like a score, how good the view is. So it's not necessarily waterfront. It can be another view. It can be a beautiful mountain. So this is the first model that we are proposing to look at. So we start with the log of a square feet of living space, and then the square feet of the lot, the number of bedrooms, the number of floors, which could be positive or negative, we don't know. The bathrooms, waterfront condition, right? A house that is in good condition probably is going to cost you more. The view, the grade. Remember, the grade was just a score for the house. The year built, the latitude, the longitude. These are kind of location type of indicators. William, will you need to first study each variable individual to check which one to apply log? No, you just need to do that for the response. The other ones, honestly, unless you have just one predictor, you can do it by your own convenience, honestly. It's not, I would try to, again, to log transform the ones that have very strange scale, but it's not really as necessary or crucial for the predictors. Okay, you just have to remember what the interpretation is if you're taking the log. No, Sebastian, you don't need to apply it to the predictors. You just need to apply it to the response. So the exercise is asking you to provide interpretation for the coefficient of square foot of living space and waterfront. So let's see the results. Now, the variables in this model that are categorical appear in the table inside parentheses, and after a letter C that stands for categorical. This syntax comes from the software library we use to fit the model. So in this case, what can we say? Well, the R square is considerably improved. It went from 0.45 to 0.76. We will talk about how do we select the variables in a bit. R square might not be the best criterion that we are going to use. So we're supposed to interpret square feet of living and waterfront. All right. So how do we interpret this? So the coefficient is 0.4. So what is the interpretation of this coefficient? Viviana, excellent. One increase of 1% in square feet of living space. So we are working with percentages. Why? Because it's the log, leads to an increase of 0.4% of the price. All right, very good. And what about, which one was the other one? Waterfront, which is this one. How can we interpret this? Yes, Herman, it's perfectly possible that the intercept is negative because we have transformed the y variable into logs, and the log can be negative. Ahora, if the house has a waterfront, the price increases by 39.9%. Excellent. So there are interesting questions that are coming up here. Why the bedrooms have a negative effect? Well, keep in mind that here you have the size of the house that is playing a major role in predicting this. And so some of the effect of the size effect is captured by that. There could be houses that do not necessarily have a large number of bedrooms, but they have other amenities that make them large, and the number of bedrooms doesn't really help. So you might have a house that has many entertainment rooms, or that has a gym inside, and so on. So it's there is also a problem of omitted variables. That is, there might be other variables that we are omitting, and that is biasing the estimation of the coefficient. Also, you might have that a location type of effect. The most expensive houses might be located in areas that are very densely populated. And those places probably they don't have a high number of bedrooms. Could be, right? So there are many different things. So from what we can see here, all the variables are significant, right? And we can see because all the p-values, if we fix our significance level at 0.05, we can see that all the variables are significant here, highly significant, I'd say. And the linear model explains about 76% of the total variability, and an increase of 1% in living space leads to an increase of 0.4% in price. And a property with a water view is priced at 39.94% over 1 without such a view. Remember that here you would be, for categorical variables, you are comparing the baseline, which is no water view, so it's when the variable is 0, to when the variable is equal to 1. That means there has a waterfront. As you all noticed, for each additional bedroom, the price of a house decreases by 2.5%. This seems nonsensical, and we'll see why, okay? What other factors we might consider? Well, proximity to services, hospitals, schools, etc. And one of the most important parts is location, as you all have noticed. So two houses with comparable features can be priced very differently depending on the neighborhood and the geographic position. In this case, we have two different sources of geographic information: lat and long, and the zip code. Now, keep in mind that lat and long are typically more useful when you are analyzing something physical, a physical system, or in the environment. In a city, it's different. You do not necessarily have something that changes linearly with latitude or longitude, but we're going to try to investigate it anyway. And Matteo is saying variables named like proximity to shopping center, etc., are confounding variables. Yeah, in this case, it's a problem of missing value, really missing variable, because we do not know. We don't have these variables. And Juan Pablo, definitely altitude. Yeah, well, you know, also that could be a factor, definitely. The altitude might determine also the view and so on. All right, so now let's investigate the relationship between latitude and the log of house prices. So we say, well, you know, let's play with our geographic type of variables. And we have the following here. What do you observe? And what do you think that an appropriate transformation could be? So confounding variables is a variable that is not always missing, but you might have it, and it might be capturing some of the effect of another variable. So that's kind of a collinear type of effect. The other thing is that at times you might be observing an effect that you attribute to a certain variable, but is really there is a causal effect with another variable. So the issue of confounding variables has to do more about the causal relationship. In this case, we are not really looking at a causal type of effect on this particular model. I prefer to call it omitted variable problem in this case, because we are not including all the relevant variables. Adrian, before creating the model, joining lat and log with neighborhood data on the dataset to create a, yes, indeed. Well, that could be very interesting. However, neighborhoods might be composites in the sense that you might have a neighborhood that has different, let's say, different pockets of value, right? You might have, if you have a large neighborhood, you might have areas that are more or less expensive. For this one, we can do exactly that with the zip codes. Yes, Luis, many times when you add variables that are correlated with each other, it would definitely cause collinearity. And that's something that, you know, we will have to investigate in a different case, how to deal with collinearity and multicollinearity. Maria, is it possible to enter these variables as a matrix? Yes, it is, definitely. So what do we see here? Is it an obvious transformation? It's not very obvious to me. Y cube, sine of x. Don't you notice though that it's more that there is an area, right, where the price doesn't seem to change. For certain latitudes, it doesn't change at all. And then it has kind of a hump for another set of latitudes. So this would be definitely something non-linear. Perhaps a function that is like a step function where this is constant and then it has a little quadratic kind of thing. Yeah, definitely not obvious. Yeah, Luis, that's what I was suggesting to make it discretized. A sigmoid, Matteo, yeah, that's possible. However, the sigmoid typically, you know, reaches an asymptote and so if we think now, one could make a choice of this type and say, well, the majority of the points are here. So since I cannot really have a function that is simple, okay, I will just say, okay, well, I will like to try to capture as much as possible of the hump. So one thing to do, it could be to use a square term, right? So what happens if we add the square to the linear model? Well, if we add the square, definitely, well, obviously we expect a negative coefficient because you have a concavity that we have a concave function. And yes, we find that this coefficient is highly significant. And R square, what happens to R square? R square is increased because it went from 0.76 to 0.778. Not a huge increase, but notice that the longitude now is actually not significant anymore, which is kind of interesting, right? We were able to capture that kind of hump on the curve, on the relationship, which, by the way, might stay there or might be removed once we consider the effect of the other variables, okay? Some of you have looked at the residual and said, the residuals don't look normal. I say, yes, because we have not yet reached a good model yet. We are still working through it. So another question for you. Yeah, well, actually, I kind of give you already the answer for this one. And so we can go because, you know, we discussed the R squared, etc. So exercise. One of the properties of R square is that it can never decrease when the set of predictors is increased. So you add more predictors, R square is going to increase. So you want to add variables that have nothing to do with your data set, R square will probably increase just because you might get lucky and find some additional correlation. Worst case scenario will be stay the same, which is impossible, almost impossible. So what's the drawback then to use R-square as a model selection criteria? Natalia, why we use lat and lat square at the same time? Because if you think about the equation of a parabola, you have y equal to a plus bx plus cx squared. So you have both the linear term and the quadratic term. Jorge, very good comment. Overfitting, indeed, that would be one of the major issues. Plus, we would be increasing the variability of our estimates of our predictions. Remember, when you hear the word garbage in, garbage out, yeah, if you're estimating variables that provide nothing, or they give you a false sense of security, if you then try to use those to predict, chances are that your predictions are not going to be good, right? Also, the model will become unnecessarily complicated. So what do we want from a model? We want a model perhaps that does not overfit. So we want a model that is parsimonious, right? That can provide good indications with small number of predictors. That's true. However, when you have a very large data set, this is not very large, but when you have a larger data set and more information, if the variables are good, you should include them, definitely. If they are significant and they are providing explanatory power, absolutely, especially if you can interpret them well. So selecting the appropriate set of predictors is a very important problem in linear regression. So we cannot just look at R-square as the purpose of as a criterion to maximize. And also, we have to try to be mindful about what we want to try to include. We want a set of predictors that can generalize well as well, to other data sets, right? And one way to address this issue is to have a penalty for the inclusion of each additional variable. That is, what we want is to say, okay, we know that the fit is going to improve if I add a variable. If we, however, is it improving enough? So the inclusion of a variable should come with a cost that is justified, right? It's going to should be worth it to include a variable. And this is what the so-called model selection criteria provide. The most famous one is called the Akaike Information Criterion, or AIC, that has a term that rewards for the fit. So the better the model fits the data, good, you get rewarded for that. But then there is a penalty term for the parameters, for the number of parameters. So in order for a bigger model to give you an advantage and to optimize AIC, R-square will always improve. AIC may or may not. Now, R-square, unlike the AIC, unlike the R-square, is a criterion that you want to minimize just because of the way that it's built, okay? In fact, the AIC is defined as the negative log likelihood multiplied by 2 plus 2 times the number of parameters. And that's because of the distribution, because of distribution theory and so on. But when we optimize AIC, we want something that is as small as possible. So if you have -2 next to the log likelihood, the better the model, the more negative this number will be. And then the +2 times the number of parameters is the penalty term that will make it less negative or less small. So When you are comparing different models for the same response, of course, the one with the lowest AIC is always preferable. Yes, if you torture your data enough, it will confess. That means that if you really, really try hard to mindlessly get the answer that you want to get, you would get it, but that would be completely unethical, right? So AIC is a number that appears in these tables, and that tell us whether or not the model has improved or not. So this is the model with the square term, and we have AIC equal to 1086. We'll talk about what this means. In the previous model without the square term, we had an AIC that was 2524. So that square term actually was extremely important. Why am I saying that? Well, the reason why I'm saying that is because it's a very large difference. Two models are comparable when their AIC is within a variation of 2. But in this case, we are talking about a variation of 1000. AIC does not mean, by itself, doesn't mean anything. AIC makes sense only when you are comparing it with another AIC from a different model. Christian, if we start adding 1, if there is no significance, we pass to try 2 variables and continue until you get, well, if your criterion is based just on significance, what you're proposing is a forward inclusion. There are different ways to select variables. There is backward elimination. You start with all the variables and then you start eliminating the ones with the larger p-values. And then there are other strategies that actually look at all the models, all possible combination of variables, and then they select the one with the best AIC. However, remember that, as I mentioned, when AIC, 2 models have a very close AIC, let's say between +2 and -2 within each other, that means that they are very comparable. They are almost indistinguishable. When the delta is of 4, then we would say that they are moderately different. And it's a substantial difference when the difference is about 8. Yes, for the second model, in this case, it was an astounding reduction. So very crucial term to include. So the model with the square term is preferable. So notice that we are not considering all possible variables. We are not like looking at other transform. We are just doing some of it. This data set can provide so much fun and entertainment. You can come up with models that are better than the ones that are presented here if you explore enough, okay? And sometimes it's good if you're actually coming up with meaningful models. Now, let's talk about waterfront and how it interacts with latitude and longitude. This might be working in tandem, right? Let's talk about what interactions are. If we want to measure the effect of one variable for a specific subclass of a categorical variable, then what we do is and say, okay, the question that we might have is, we saw that latitude changed the price. One question that we can ask is the effect of latitude and latitude square, does it change for properties that are closer, that have a water view compared to the ones that don't have a water view? So are we really capturing something that is more specific to water view or not? So for this reason, we need to introduce interaction terms. So this is equivalent to run 2 separate regressions. One for the group that has waterfront and the other one for the group that does not have a waterfront. So here in blue, we see, of course, that the houses with waterfront are a minority, and they are the dots in orange. And the ones that don't have a waterfront are actually the majority. So if we were just using this single predictor with interaction, we would see that these two lines actually have a different slope. So the effect of latitude seems to be more accentuated for the houses with waterfront, which is somewhat interesting. So what is the interpretation of this interaction? It means that for the subgroup of houses that with a waterfront view, the latitude has a steeper slope compared to the log price. That is, for a small increment in latitude, the change in price would be much larger for houses that have a waterfront view. Now, in order to fully interpret this, you should really get a map of Seattle and actually do a spatial type of analysis, which requires more sophisticated methods, but also really look at, okay, where are the houses that have a waterfront view? And then think in that term. Viviana, I completely agree with you. It's not the same being in front of the river in Bogota compared to the ocean in Santa Marta. Location interacts with waterfront, definitely. Now, this is a plot, on the other hand, that is looking at the effect of latitude for different view indexes. What can we see in this case? Notice that here we had a different intercept, definitely, and a different slope for these two lines. What do we see in terms of the interaction between view and latitude? So here we are looking at different qualities of view, not necessarily waterfront, right? Maria Paula, ASC improves compared ASC corrected. The ASC corrected is actually very similar. You see a difference when you have small samples. In this case, you will not see that much of a difference because you have a very large data set. All right, yes, I appreciate your comments here. We can see that the slopes are actually very similar for different levels of view. And so the effect is purely on the intercept. That means that there is a fixed effect of the view, but then the interaction with latitude is not significantly different. But we can also see that houses with better view have higher prices. Can you see the purple line? Is the top line. The second one is the red one, the one with a score of 3, etc. So a degree of increment in latitude increase the price of a house at almost the same rate because the slopes are very similar. So we can conclude that view of the house likely does not interact with the relationship between price and latitude. So price and latitude will be probably mediated by the interaction of waterfront and latitude. Okay. John, yes, there are many books. There is one simple book that we require using R is Spatial Data Analysis using R, is published by Springer, and the authors are Bivant and Gomez Rubio. Look it up. If you look on the internet, you will find the reference. Ornella, maybe just the fact that it has some type of view, it increases the price. Well, you know, it's more than that, because we can clearly see that it actually seems to be like a gradual increase on price depending on the quality of the view. So that's actually, we are getting something interesting out of this. And so definitely the view should be included. Sebastian, how can we check if there are interactions between many variables? Well, that becomes very, very tricky, because the interpretation gets lost. When you start looking at nonlinear interactions between variables and so on, probably the linear regression stops being your method of choice, and you start looking at other methods like XGBoost, random forest, and so on, that actually look at very highly nonlinear functions of your predictors. So, but I would say use the linear regression when you have something that is interpretable, that can be complex, but not too complex. For instance, in a case when you have, let's say, hundreds or thousands of predictors, become extremely hard to look at interaction about all possible pairs, right? Penalized regression can be sometimes of help when you cannot choose, but yeah. All right, so we can verify the finding of exercise 8 by adding an interaction term to our linear model. So we do this by adding a multiplication term. That's the way the interaction enters. So a simple model would be the log of price equal to beta naught plus beta 1 times waterfront plus beta 2 times lat plus the interaction term. And here you have a little bit of math that you can go and look at, but you know, we still have ground to cover, and I want to look at this. But so what we have here is the model that we estimated exactly here, right? So with two intercepts and two slopes. The first intercept would be the intercept that is related to the baseline, which is -68. Okay. If you have a waterfront, the difference between the baseline and the waterfront intercept would be 102. So a total of the intercept would be -168. That means that the model that you will have to adjust by 102%. So the price is twice the amount if you have a house with a water view. Compare if you have, of course, this would be at baseline, right? Now, keep in mind that this is a simplified model because it does not include all the other predictors. But also we can see here that the slope is 1.7, and the difference between the slope for the waterfront group and the non-waterfront group is 2.1. So this line, we have a slope of over 3, right? Christian, typically we look at the maximum of 2, sometimes at 3. If you have a small set of predictors and you can interpret a 3-way interaction, that's as much as I have seen. I have not seen ever applied interaction more than 3 variables, typically 2. So the 2 slopes, notice that you get 1 slope for free, which is the baseline. So for the non-waterfront is 1.7. The slope for the waterfront will be 1.7 plus 2.1. So this acts like a contrast, like a correction factor. So the price of house should increase by 1.7% among houses that do not have waterfront, and by 3.87 among houses with waterfront. Now, let's consider a model with interaction between latitude and view, which is what we had seen before. as you can see, the slopes, the interaction term, are not significant, right? Which we are not surprised, because all those lines look parallel. David, I understand the slopes are different for the linear model. You understand why we multiply? That's the way you build the interaction. So basically, if you multiply 0 times the variable in the interaction factor, it means you are not applying any correction. If you have 1 times the variable, that's the correction specifically only for those that have waterfront. So now let's use what we have learned about interaction into the bigger model that we started estimating. And then we're going to look also at AIC, if indeed has improved. And just because we want to feel very adventurous, we want to also add a zip code as a categorical variable, and whether or not the house was renovated. So we are including variables, other variables that make sense. Plus, we are also looking at latitude and latitude square. And we have the following output. Notice that R square has increased a lot through the roof, no pun intended, 0.88, increased a lot. And the AIC became negative. So we have a lot of improvement done here. So it's not surprising, because when you have a large data set, you have the luxury of adding really a lot of variables. So the model now is somewhat complicated to interpret. Notice that almost everything is significant. All the zip codes seem to be different. And although we are all comparing to one of the zip codes, but definitely seem to provide a lot of information. Bedrooms is still negative. That hasn't changed, but be patient for that. The elasticity is still 0.42. So that has not changed that much, remember. And the year built is actually negative. So what we are saying here is that the more recent the house, the lower the price. What would be your possible explanation for this? Kimberly, in which case it's better to add the position variable, latitude, longitude, instead of, for example, the neighborhood? Well, when you have a clear, how to say, Seattle is on the coast almost, right? So you probably have a longitude effect that could be possible, but it makes sense when you have like kind of a gradient or a different, a definite gradient in terms of income, let's say. Imagine that the richest people live in the south of the city, that it would make sense to also add a linear term. Sebastian, do you have to include the variable in level and the interaction, or just the interaction? Always include, is recommendable to include the variable in levels as well. Ornella, older houses used to be bigger, so the new ones are, oh, okay, well, that's a possible explanation. Or the possible explanation could be that older houses are more historical, and so they carry a higher price because they have a historic value. Anyway, we can see that both waterfront view and renovations have a positive effect. Where is renovation? Here it is. They have a positive. So if a house, regardless of their age, if the house was renovated, we can see that the price tends to increase. Mauricio, I don't understand the zip code coefficient. That's a categorical variable. So each zip code is getting an effect. So for instance, there is a zip code, there is the I think is 98001, that's the baseline. So we are saying that this one, you expect the price, if you move from one zip code to the other, the price will be adjusted by 0.02%. For this one, it will be less, and so on. So each zip code will have a correction that is typical of that specific area. Notice there are many zip codes here. Another thing that you can do is, so far we have looked at global effects of independent variables, irrespective of the value of other variables. However, we might ask if the effect of a waterfront view is different for houses that were renovated compared to the ones that were not. So here we have the interaction between two different categorical variables. So how can we answer this? Through an interaction term. So we are going to look at waterfront and interaction between waterfront and renovated. And we can see that this interaction is actually significant. So what we are observing is that it seems that there is a small difference for properties with a waterfront that were renovated versus that were not renovated. So the difference in slope will be 0.09, which is somewhat small. And this goes to correct the effect of the of waterfront. Abraham, zip code and lat and long is not a collinearity, not necessarily, because these are linear terms, but the zip code might carry a spotty type of function, might be completely nonlinear. So you might have a general trend, like you say, okay, do houses become more pricey as we go north? So they do not necessarily, they are not necessarily collinear, especially because zip codes tend to be also shaped differently. They have different areas and so on. So exercise 10, the AIC for the baseline model was negative 12,000 and the R squared was 0.88. Let's expand the model by doing the following. Adding a term which accounts for the square of the year the house was built. And adding an interaction term for the presence of a basement in affecting the relationship between the longitude coordinate and the price of a house. How can we do this? So the first one is essentially asking you to say, okay, is there a nonlinear effect of year to be built? So imagine that there is a particular time in history where houses were built very well, or that they were very good houses. Then you probably would expect that the price would peak and then decrease, right? And what if we had an interaction term for the presence of basement to justify the longitude? So you might want, in this case, an interaction between longitude and basement. So these are like sort of out there. They're a little bit crazy questions and say, why a basement should interact with longitude? Well, let's see what happens. This is the table for the model with the ER square. Is there an effect of year? Well, it seems that there is. And we see that this term is highly significant. And this is the model with the interaction between basement and longitude. Again, these are only some of the models that you can actually create. There is not a specific. We can see that the effect ended up significant in both cases, and both models improve the fit. R squared becomes higher and AIC becomes lower in both cases. If you want to compare these two models, these additional variables, which one would you choose? Well, you would choose definitely the one that has the the smaller AIC, which is the model where you add the year square. So cannot believe it. We finished exactly at 9:50. That was the, I think it was the time of the break. But let me say something about conclusions. We applied different types of transformations to the independent and dependent variables to improve the quality of our linear model fitting, but also to answer specific questions. For instance, how can we capture a nonlinear effect of a predictor? Or how can we reconcile our response variable to the hypothesis of a linear model? And also, how do different variables interact with each other? So we integrated what we were observing in the exploratory data analysis, some of the scatter plots that we looked at, and to also improve the relationship that these predictors describe with respect to price. These are some takeaways. So these are the key points that we want to remember before we go and study the details. Transforming the dependent variable can improve linearity and solve the problem of uneven variance. So you obtain two different advantages. Transforming the independent variables can improve the quality of the fit, capture nonlinear types of relationships, and test different hypotheses. Also, we learned that R squared, since it always increases the more variables you add, is something that we should look at with a little bit of caution because it can lead to overfitting. And then we learn about interactions. There are particular type of variable transformations that are the product of two or more variables. They can capture the variability in relationship between an independent variable and the dependent variable based on the value of a third one, for instance. And then I will let you explore the relationship between log transformations and percentage type of interpretation. So thank you for your attention. I need a little break. You all need a little break too, but we will be back together to dig into the coding aspect of these linear models. Very easy, but I think that you worked really hard and you stayed awake and participating throughout the case. So thank you so much.